All right, everyone, we are in our two-dimensional kinematics notes, and what we're going to do here is we're going to be basically looking at how to solve example number 2. All right, so here we are at example number 2. We have a golf ball. It's hit with a velocity of 33 meters per second at an angle of 40 degrees above the horizontal. So again, I want to note that we're dealing with a velocity here. And the velocity we know, of course, is a vector, so it has both a magnitude, that's the 33 meters per second, and an angle, or a direction, I guess in this case. Since we're dealing with a two-dimensional kind of thing here, of course, this is going to be some amount above the horizon. We want to know how far does the ball travel horizontally while it's in the air, and we're making the assumption that it's going to land at the same level. Okay, so we're going to think about what that means. And the second question says, what is the maximum height the ball will reach? So what I'd like you to do here is go ahead and stop and think about how you might actually go and solve this. We of course know that we have the words to describe this, and the next part that we're going to actually do is take the situation from the words and put it into our picture. So when you've done that, let's come back to me and we'll kind of continue from there. All right, so here we are back at our picture, and there's 3 snapshots of interest, I believe, in this problem. If we think about what we're being asked here, of course, the position where this ball starts, where it's first struck, and we know it's given some velocity above the horizon, so it has to be traveling upwards in this case. We also are asked in part B, we're asked to find something about how high is this ball? So part B asks us about a snapshot here at the very peak of the motion. And I believe part A asks us something about how far did this thing travel? So in this case, what we're dealing with is the distance. This is a horizontal distance, of course. That would be what I have labeled here as delta x. From our initial snapshot until when it reaches the ground. Again, this is at the same level, you'll notice here. So, of course, we're dealing with a situation where there's no air resistance, so the only acceleration is due to the force of gravity. Force of gravity, of course, is that force that's in the downwards direction. We have our acceleration right here is due to gravity, so that's 9.8 meters per second squared. Here's kind of an important thing. We know in the very top of the path, the ball stops moving in the y direction. Again, notice what I said there. It doesn't stop moving at all. It still has an x velocity. That x velocity hasn't changed because the force doesn't act in the it doesn't act in the x direction, but it does act in the y direction, so it's changing the y component only. Since we're wanting to know in part B, how high does it go? That's from the starting position down here at the ground up. So that's why my delta y, which is what my part B is asking for, is labeled right here. And of course, when it gets back down to the ground, it does have some velocity in the, I'm going to say this is in the below the horizon direction. I don't exactly know what direction it is, but I know it's in this direction somewhere. It's got to have some x velocity, but it's also got to have some y velocity here as well. All right, so let's see what I've done here for knowns. Looks like for part A, I'm dealing with from snapshot A over to snapshot C. So the knowns that you're going to see here are reflective of those two things. In the x direction, looks like my initial velocity, or my original velocity, is 25.3 meters per second. And you might ask yourself, how in the world did I get 25.3 meters per second from the initial velocity of 33 meters per second? So I'd like you to stop and think about that for just a moment. Where did that number come from? When you think you know the answer, come back and we'll talk about it. All right, so we're back looking at the initial velocity here, or the original velocity. And again, we know that it is some angle of 40 degrees above the horizon. This is telling us that there is some x velocity to this, and there is some y velocity. So the 33 meters per second is this hypotenuse right here. if we want to put a number down in here for the x direction, we can't put the 33 meters per second in, because of course that's a combination of both the x and the y. All right, so let's see how I actually figured this out. We know that, again, the component found here, this is if this is our angle, this would be the adjacent side. The adjacent side relates the adjacent side is related to the hypotenuse through the cosine function. And again, what we end up with here is the x component would be equal to 33 meters per second times the cosine of 40, which that's where this 25.3 meters per second is coming in. Likewise, the y component for the original velocity is based on the sine function. Again, our y velocity looks like this. That's the equivalent to the opposite side of this triangle, and therefore we're going to end up with 21.2 meters per second here after I've used the sine function. Sine function relates the opposite to the hypotenuse. So that's where we're dealing with our original velocities. Since I've called down positive, the original velocity in the y direction is an upwards velocity, so it's going to be negative. The final velocity in this case is, because we're dealing with a situation where you have symmetry, we know that it's in the opposite direction but equal in magnitude. My delta y from the very start to the very finish, because it ends at the same level, that means that there is no change in the y. So that's why my delta y is 0. Now what I ultimately hope to find here is my delta x. So I'm going to have you go ahead, stop and think about it for a moment. When you, what we've done now is we've taken words, put them into pictures, and now I want you to come up with the equations to solve this. All right, so we are back. We're going to look at the equation that we are going to take a look at here. And since we're looking for an x direction thing, it would be an obvious choice to look in the x direction for an equation that works here. Now, I will promise you, you can go through all the equations you want, but we are not going to have an equation that helps us. The reason is because we're missing time. So the first goal here is to actually calculate time, and again, using the x direction is not going to be successful. So what we're going to do is I'm going to pull this over here. We're going to take a look at how to find the time. I have used the y direction, and our v sub f equals minus v sub o plus at. Again, notice the directions here. Final velocity was a positive because it's down. Original was negative because it's up. And the acceleration is down, so it's positive as well. Solving for t in the y direction will give us the time that this ball's in the air. Well, the time the ball's in the air is also the time that it takes for it to travel from the left to the right. So this time is going to end up getting substituted into an x direction equation. In this case, I chose our quadratic formula. Our acceleration in the x direction is 0, so this term right here, this 1/2 at squared, cancels out, and we're left with the displacement equals v sub o times the time. Since our time is from the y direction, we just make the substitution right here. After we've done our substitutions, again, this it's important to keep in track of what you're dealing with here. The v sub o in the front is from the x direction, and the part that we substituted in right in here in the parentheses is from the y direction. So you'll notice the y direction stuff ends up right here, and the x direction stuff ends up over here. We are asked what distance, I believe, did it go. Let's pop on over here. How far? Far would indicate a distance, not a vector kind of answer that we're looking for here. So in this case, we do not need a direction for the final result. All right, so let's take a look at what we're being asked to find in part B. Part B, we now actually are looking at the height that it reaches. So we're now looking at two different snapshots, okay? So we're looking from snapshot A to snapshot B. So be careful here. Even though we have just found a delta x, be careful that you don't substitute that delta x in here. However, due to the fact that this is symmetrical, we may be able to take advantage of the fact that the delta x we just found is actually twice from the A to B. So in other words, maybe say that again. A to C is what we just found. We know that A to B, and I don't have that vector drawn here, but it would be half that total amount because of the symmetry. So that's something we may find to be useful. So here's what I want you to do. Stop and think. I'd like you to take our picture here and figure out what equation might help us find part B of this problem. All right, so the equation I chose was our VF squared equation. At the very top, which is where our final velocity is in this, again, we're dealing with snapshot A to B, so our final snapshot is that top snapshot. So the final velocity here is 0, so it cancels out. Our original velocity in the y direction is a negative, so we have that there. Our acceleration is positive because it's down, and our delta y is negative as well. Doing some algebra to isolate our delta y, which is what we're looking for, we end up with v sub o squared divided by 2a. Substituting numbers in, and again these are y direction things, we end up with 22.9 meters. And again, we're not being asked for a vector here. It doesn't ask what is the displacement. It asks for a distance or what is the total height. That's a scalar kind of answer. So the height here is 22.9 meters. Now the problem does not ask us for this, but I'd like to ask the question now, what would the final velocity be for this? Now, when I say final velocity, let's talk about the final velocity at point B and the final velocity at point C. So in a sense, I'm asking for instantaneous velocities. At the point B, what is the velocity? And at the point C, what is the velocity? So let's bring our picture back up here. Here it is. I want to know what's the velocity here and what is the velocity here. I'd like to stop and think about that, and when you think you have an answer, come back. All right, so here we are. The questions were about the velocities at this point right here and this point here. So let's actually think about this conceptually, what's going on. As the ball travels through the air, and maybe traveling through the air is not the correct way to say it, because if there's air, there's going to be air resistance. Let's just say as it's traveling, there is a force acting on this, and this force is the force of gravity. And that's the same force that acts on this ball the entire time. It's this force of gravity that acts in a downwards direction. We of course know that when there's only this one force acting on it, we have an acceleration in a downwards direction, and of course this this acceleration is an acceleration due to gravity. So the only acceleration is in the y direction, and that's only going to change this y component. So our x component is going to remain the same this entire time. So at the very top, at the peak of here, we know that the ball has to stop moving upwards. So the velocity in the y direction here is a 0 meter per second velocity, but it still has this 25.3 meters per second velocity that's going to keep on moving it to the right in this picture. So if I would say the velocity here, I'd say 25.3 meters per second in a horizontal direction. Down here, again, we can use the idea of symmetry. We know this 25.3 is still here, and it's going to gain back the 21.2 meters per second. That, of course, will add up vectorly speaking. I'm not sure if that's even a right word, but it's going to be 33 meters per second, and it's going to be at an angle of 40 degrees below the horizon. And again, this is that idea that we're going to have a very symmetrical kind of problem here because of the fact that it's at the very same level.